Let's look at some applications using derivatives of exponential functions, specifically with a base number e. The demand function for a product is modeled by p equals 79 e to the negative point. Be very careful when you copy this down. There's 4 zeros and a 25x as the power, where p is the price per unit in dollars and x is the number of units. I copied this one right out of WebAssign, but you really be mindful of how many zeros there are because that's real easy to lose one of them. What price in dollars will yield a maximum revenue? Round to the nearest cent. Okay, so revenue, we can build it by multiplying x times our price function. So that's going to be x times 79 e to the negative 0.0000, however many there are, 25x. From here on out, I'm just going to say e term. So distributing x, that's going to be 79x times our e term. This will let us use product rule because we have an algebraic term times an exponential term. Remember, with product rule, it's derivative of the first term, that's 79, times the second term left alone, plus first term left alone, times the derivative of the second term. So with e, you make an exact copy, and you multiply it by the derivative of the exponent. On the second line down in purple, maybe magenta is a better description, I'm going to recopy this first term. That's the first part of product rule. 79 times this long negative decimal number gives us another long negative decimal number. This x stays the same and this e stays the same. All I did was combine the 79 and that last number. Now, in this third step, I'm going to factor out the e term because they're identical. It's identical for both terms. So I'm going to factor that out. That's going to leave a 79 and a negative this number and x. Now, the reason I wanted to factor out the e exponential term is because it's never equal to 0. If you were to actually take a graphing calculator and graph this function, it would never touch the x-axis, so no value of x makes it 0. That means we can ignore it. Now this other factor, 79 minus 0.001975x, if we set it equal to 0 and solve, then we actually get a value of 40,000. So that's the number of units that maximizes the revenue. It's a critical number of your revenue function. So have we answered what the question asked? Not yet. What price in dollars will yield a maximum revenue? We found with that 40,000 number, that's how many units that will maximize revenue, but we're asked to find the price. So what we'll do, and I changed ink to a light blue, is using the price function in the very beginning of the problem with 40,000 units subbed in. That's going to give us 79 times e to the negative 0.4025 times 40,000. We substitute that number in for x. Using your calculator, we get $29.06. That will be the price that maximizes revenue. So first, we built revenue. Then we found the change in revenue, and it's maximized at the critical number. Critical number occurs when the first derivative is 0 or undefined, but we don't have that case here. We just have 40,000 units. That's where our revenue is maximized. And then we go back and use the price function, the demand function, with 40,000 subbed in, and that gave us this price of $29.06. Now there's a part B to this problem, and it asks what's the maximum revenue in dollars at the price found above. So remember that revenue is x times price, x times p. So if we sub in 40,000 units for x in both locations, then we have 40,000 units times the price at which they should be sold, that's $29.06. Multiplying number of units and price gives us a maximum revenue of $1,162,400. This second example is just a repeat of the first example, but the price function has been changed. These take a little bit to get used to. So this is our price function, the demand function that's given. P is still in price per unit in dollars, and X is a number of units. Again, it's the same two questions. What price in dollars will yield a maximum revenue, round to the nearest cent? So again, building revenue, that's X times P. So if you multiply X times your price function, you get 72X times the exponential term. Taking the first derivative, because if we're going to maximize revenue, we want to know where the first derivative has a critical number. So our first derivative, and then also don't forget this, we are going to be using product rule again. That's our first term. The exponential term is our second. So the derivative of 72x is 72 times the second term left alone plus first term left alone times derivative of the second term. And just like in the previous example, with e, you make a copy times the derivative of the power. Multiplying, let's see, this one I'll try to be a little more efficient. I factored out a 72 and an e term because both terms have a 72 and an e term. Factoring that out, because the first term is identical to what we're factoring out, that leaves a 1. Then, if we factor out a 72 in this exponential term, that leaves this negative decimal times x. Negative decimal times x. Recall that the e term is never 0. No matter what you put in for x, this will never equal 0. That's just one of the properties of exponentials when you don't add or subtract a constant. This factor can be set equal to 0, and if we add this really negative decimal over and then divide by that coefficient, we get 40,000 units, which happened to match the first example, but I want to do a couple of examples just so you'd see two of them in this YouTube video. Recall that 40,000 is just the number of units that maximizes revenue. It doesn't really answer our question. Part A wants to know what price will yield a maximum revenue. So we use our price function from above. Go back up here to your price function, grab it, plug 40,000 into it, and just be careful entering this exponent. It's e to this product, and it'll be $26.49 per unit. That's the price that should be charged to maximize revenue. What is the maximum revenue in dollars at the price found above? Again, revenue is X times P. So 40,000 units was X. Price is $26.49. So if you multiply the number of units times the price, that's your revenue, $1,059,600. All right, let's switch gears, and this is still going to be an application of a derivative of an exponential function, but it is more of a banking type application. The balance A in dollars in a savings account is given by A equals 5,000 e to the 0.08 t, where t is measured in years. Find the rate at which the balance is changing when t equals 1 year, 10 years, and 30 years, round to 2 decimal places. Okay, so rate at which the balance is changing, that tells us to take our first derivative. That's rate of change in the amount in the account. So we have 5,000 e, make a copy of your e, times the derivative of the power of e, which is 0.08. 0.08 times 5,000 is 400 times our exponential term. And so this equation here, our first derivative, that's the rate of change in the savings account at any given year after opening. So that's where our t is variable. Okay, so we were asked to find the rate of change when t is 1, 10, and 30. So using this first derivative, if you plug a 1 in and use your calculator, you will get $433.31 per year. That's the growth rate of the savings account at the first year of maturity. Then the rate of change of the account at the 10-year mark, you plug 10 in for t, same derivative, but you just switch out the t value. Carefully calculate that, you get $890.22 per year. And then finally, the rate of change that the balance is changing at 30 years is $4,409.27 per year. And again, that's replacing t with a 30. And that's why it's important while you're young is to start you a savings account, specifically like a retirement account. Try to get a job that has the retirement benefit. Put as much into your retirement account as you can at an early age so that it has a lot of years to mature and grow, because you can see first year compared to 30th year how much faster it's growing. So if you can get something like that started in your early to mid 20s, even upper 20s, that's about, I think I was 26 when I first had a good retirement plan. That way it gives it plenty of years to grow while you're working. Also, the more you're able to contribute to your retirement account, the lower your taxable gross is each year that you're taxed on, because the amount you put in retirement is not taxed until you start drawing it out years later. Anyway, you guys, I'm not by any means a business expert. I just do encourage you to start your account soon. Put as much as you comfortably can into it and just let it ride. Let's do one more example. The balance A in dollars in a savings account is given by 4,000 e to the 0.06 t. T is still measured in years. This is just a second example. Find the rate at which the balance is changing when t is 1, 10, and 25. So main thing is getting our first derivative calculated correctly. That's going to be 4,000 e to the 0.06 t times 0.06. Don't forget to use the derivative of the power, and you chain it to the end. Well, 4,000 times 0.06 is 240. That's where this 240 comes from. It's 4,000 times the derivative of the power, which is 0.06. Now, just like we did in the previous example, we're going to take our first derivative and we're going to sub in a 1, 10, and 25. Carefully calculate. So when you sub in a 1, 240 times e to the 0.06 times 1 to the nearest cent comes out to 254.84. That's the rate the account is growing after the first year. After 10 years, you simply sub a 10 in here, calculate, and that's growing at $437.31 per year at the 10th year mark. And then finally at 25, substitute 25 in, and you get $1,075.61. That's the growth rate of the account at the 25-year mark. But they do grow exponentially. I hope this video helps out. Reach out by phone or email. If you're on campus, stop by the office. I'll do my best to help you out.